All right. Okay, so we're sharing because this camera that we have can't see anything. So I'm going to try to type most everything on here. Okay, so chapter 25 is the chi-square test of independence. Okay. So here's what I would like to do. I just want to do an example. We're going to go through our same 7 steps, but the formulas are going to be very different today. And so let me just give you, this is fake data based on a true story. Okay? This story took place at the University of California at Berkeley. A lawsuit was filed. Yeah, about time. You're going to wait until you hear what the thing is, and then you'll be like, ooh. All right, so we're going to just pretend that a university, an unnamed university, offers 2 degree programs: electrical engineering and English. Admission is competitive, and women expect discrimination. Okay? Is it fair to conclude discrimination? Okay? So here's what they give you. Admit, deny. We got males. We got females. We got 35 and 45, and we got 20 and 40. I'm going to make this a nice table. We'll center it so it looks nice. Okay? So you all are almost done with this class. This is one of only 2 chapters we have. So I'm just going to throw this out here and say, you're the statistician. Somebody gives you this data. What would you do with it? Does it look like discrimination is going on based on this data? What would you do first?
Make a graph.
Make a graph of what?
Of the male and female commitment.
Okay, now, that's not a bad idea. However, you just broke one of my rules that we learned clear back in chapter 1 or something, whenever we did graphing. Is it good? Oh, by the way, this is another important thing that you should remember on your project. Is it good to graph raw numbers? Jordan's shaking his head no, because it's skewed. It could be skewed. What do you think, Sandra? Because? You wouldn't get an accurate graph because? A histogram? Can I do a histogram on this kind of data? What kind of data do I have here? What did you say?
Bar graph.
Central bar graph. A potential bar graph. Bar graph rather than a histogram, is that what you're saying? Why would I choose a bar graph instead of a histogram? What kind of data do I have? Here, we'll answer question 2 right now. What kind of data do I have? Why is it categorical? You got admitted or you did not get admitted. Okay, so this is categorical data. Okay. Now, normally with categorical data, what do we do? Z or a t-test? A z-test. Okay. Now, just so you know, just for background information, a chi-square test, notice it's squared, is actually a z-test squared. And it works on categorical data. Okay? Just background information. But we're actually going to do a chi-squared test today. Okay? Now, let's back up here. Got our data here. It's categorical data, so we can't do a histogram. Should not do a histogram on this data. And y'all have forgotten my very important phrase, except for Alex maybe. Should I graph raw numbers? No, because no, wouldn't have outliers in that, not necessarily. Well, I won't say won't, but that's not the reason. Because you either got admitted or you didn't get admitted. You wouldn't call that an outlier. Rates are better than counts, right? Now, do you notice how many men were admitted versus how many women? You probably would want to get a total, right? Okay. So we've got 80 men admitted, or excuse me, I should say applied. We've only got 60 women applied, right? So there's fewer women. Well, of course, if there's fewer women, of course there would be fewer admitted, right? That seems fair, doesn't it? Okay. But how would I figure out the rate of admission? You can shut it.
The ratio.
Okay, we did a ratio or a percent admitted, right? How would we figure that out? 35 over 80. So 43% of men were admitted, 33% of women were admitted. Okay. So, women, we've got two of you here. Bettina, what's a 10% different? Does it look like the admission rate is discriminatory against women? It kind of looks like it might be, right? But what would you say about my sample size, Sandra? Well, it's pretty small, right? How many, I guess if we add these up here, we've only got 140. That's not very big for a poll, right? Okay, now let's talk a little bit about sample size. This one, so what are my two rules so far? I'm going to give you a third one today. So the two rules are for categorical data, NPQ has to be greater than or equal to 10. For quantitative data, what's the rule? Something 30. Nope, not X bar, not mu.
So these are rules for categorical data?
These are sample size rules. Sample size rule for categorical data is generally NPQ greater than or equal to 10. Quantitative data, the rule is, Alex? I thought it was X bar. What? Don't know. Chandler, save me. Oh, thank you, Chandler. N is greater than or equal to 30. How did you guys forget that? Okay, now, so that's what we've learned up until today, although most of you have forgotten it. How many now remember that rule? Okay, Alex, you still don't remember it? You're still too tired to remember anything?
Yeah.
Okay. All right, so rule number 3, if it's chi-square data, and we know it's chi-square data because it's in the table, but that's going to be your giveaway, okay? Then, here's the rule. No cells can be 0, okay? That's rule number 1. And rule number 2, no more than 20% of cells are less than 5. Okay, so for example, let's pretend for a moment that I only had 4 here, 4 males. Okay, we're going to change our data just for fun. Okay, I've got 4 cells here, right? One of my 4 cells is less than 5. 1 divided by 4 is what percent? 25%. So it's too small. Can't run the chi-square test because this cell is less than 5. And now if I had a bigger table, I could get away with 1 cell being less than 5. But since I've only got this very small table, 4 cells, that's 25%, so I should not run this test. I changed it to 4 to illustrate a point. Okay? So if there was a 4 there, I could not run the chi-square test. Okay? There isn't a 4 there. All of my cells are greater than 5. I'm okay. Does that make sense? Okay? So these are the 3 rules. For categorical data, which this is actually categorical, but this is actually chi-square, okay? For the 1 and the 2 proportion tests, NPQ has to be greater than 10. For chi-square data, these are the 2 rules that apply. You can't have any zeros, and no more than 20% of them can be less than 5. For quantitative data, and it has to be greater than or equal to 3. Okay? All right. So, step number 1. Okay? Actually, here, I'm going to skip a couple of steps here because I want to go to step number 4. What's step number 4? Pick the test. And what test are we picking? Chi-square test of independence. Now, there are other tests of independence. There are other chi-square tests. We're not going to learn about them in our class. Okay? All right, because it's a chi-square test of independence, I need row and column totals. Okay? I've already got my column totals here. Now, I need my row totals. Now, let me just warn you about one thing here. Okay? Watch this. So you can press the auto sum button here. Whoops, I put it in the wrong spot. Auto sum, and it adds up the entire row. That's what I want. I press it again, it adds up the entire row. That's what I want. Let's pretend that 140 is not there. Watch what happens this time. It adds up the column. Okay? So be careful, because on this problem it doesn't matter, but on other problems it will, and it will mess up your data. So here's what I would recommend. Copy it and then paste it. And that's the safer way to go. Don't just keep pressing that auto sum button, because it'll mess up your calculations and you'll have problems. Okay? Question? Okay. All right. So step 1, you need your row and column totals for a chi-square test. Step number 2, is it quantitative or categorical? We decided it was categorical because the categories are, Aaron, give it to us again.
Categories?
Yep. Admitted and denied. Some people say male and female. Male and female are the groups, they're not the categories. Okay? Step number 3 is find what?
Step 2 is just categorical
Or quantitative.
quantitative.
And it's categorical.
Yeah.
You need the null and the alternate hypothesis. Okay? Now, this one breaks the rules. Okay? This one, rather than having an equal sign, you can actually write out a phrase. Okay? Now, so the phrase, you're going to want to use independent and dependent, but don't just write that. That's not good enough. So what we're going to say is that gender is independent of admission rate. Okay? Now, some of you will be tempted to say what for the alternative hypothesis? Yeah, you would say dependent, right? But do you think that the admission rate, like there's something biological that causes women to be admitted at a lower rate? No, it's probably discrimination, right? That's what they said was discrimination. So we never say dependent, we say not independent, okay? Because there could be lurking variables. And lurking variables could be something like, oh, we hate women or something like that, okay? It's not something biological, okay? Men can't have babies. That's biological, right? That would be dependent on your gender, okay? But admission should not be dependent on your gender. It might be, but it's not like a biological reason, right? It would be a social reason, perhaps, okay? So here, what I want to emphasize is so the null is always going to be independent. The alternative is always going to be not independent. But I need the variables in there, what you're saying are independent of each other. Don't just say independent and not independent, okay? Does that make sense? Okay? All right, pick the test, the chi-square test of independence. Do I dare write this on the board? Because it's way out of focus.
No.
Here, I'm going to write it on the board really quick. I'll try to. This is really a bad camera. Okay, I'll write it big, and hopefully it'll be big enough that you can see. Okay, there's two formulas that you're going to want to need. Okay, the chi-square test is the sum of the observed minus the expected squared divided by the expected. That's one formula you're going to need. Okay? The other formula is, okay, now let me do this, okay? And I'm going to make it a 3 by 3 because you might get a bigger table, okay? This is row 1, column 1. This is row 1, column 2. This is row 1, column 3. This is row 2, column 1, sorry. Row 2, column 2, row 2, column 3, row 3, column 1, row 3, column 2, row 3, column 3. Does that make sense?
Yeah.
Okay? Now, so here's what I do. The row 1, column 1 equals the row 1 total times the column 1 total divided by the grand total. Okay? Now this is the formula I have included. Now the problem is that's for here. Okay? If you're here, it's going to be row 1, column 2. If you're here, it's row 2, column 2. If you're here, it's row 3, column 3. So this formula is going to change depending on where you are in the table.
Can you say that one more time?
The formula is going to change based on where you are on the table. And we're going to do an example because I think it's going to make a lot more sense. Okay? But just realize I'm labeling these like this. Okay? Does that make sense? Hopefully that's good enough to see. And hopefully you can hear. I don't know if that has a microphone. You guys are going to get home and to be like, there's no sound. Oh, sorry. Hopefully, it seems like it usually works, but. All right, does that make sense? Sort of. Okay, so let's go back to here, okay? So here's what I'm going to recommend. When you do your test, so I'm going to call this table here my observed table. This is what I observed happened at this college, okay? Now, when you're doing this test, here's what I would recommend. Copy the table, and then you're going to paste it, not once, but twice. I'm going to blank out the numbers here. We're going to call this the expected table. And then I'm going to copy this blank table, and I'm going to copy it again, and I'm going to call this the observed minus the expected table. Okay? So we're going to use the second formula first. Okay? Now you can see what cell am I in?
R2C2.
I'm in, no, this one right here. Right here, I'm in row 1, column 1.
Oh, God.
I'm not counting the labels.
Yeah.
Yeah, ignore the labels. So I'm in row 1, column 1, right? Okay? So here's what we're going to do. We need to figure out, okay, so based on the null hypothesis, the null says that gender is independent of admission rate, right? So if it were independent, then I'm going to show you what the numbers would be, okay? So here's what I'm going to do. Equals the row 1 total, okay, times the column 1 total divided by the grand total. Okay? Does that make sense? Okay? Now I'm going to press enter. Where am I at now? I'm in row 2, column 1. I'm going to do the same thing. Equals the row 2 total times the column 1 total divided by the grand total. Does that make sense? Okay. Now, where am I? I'm in row 1, column 2. Okay. So I'm going to use the row 1 total times the column 2 total divided by the grand total. Does that make sense?
Yeah, that makes sense.
Okay. Where am I now? Row 2, column 2. So I'm going to use the row 2 total times the column 2 total divided by the grand total.
That was column this way.
Correct. Okay? All right, so here's what we're saying. Okay? If there was no discrimination going on, of the 80 males that applied, we would have expected 31.5 of them to be admitted. 35 were admitted, so more males were admitted than we expected. Okay? If we look again, if there was no discrimination going on, we would have expected 23.5 females to be admitted. Only 20 were admitted. So fewer females were admitted than we would have expected, right? Okay? So it does seem still to be the case that there might still be some discrimination going on, right? Okay? But once again, this is a small sample size. We've only got a school of 140 people. Kind of hard to tell, okay? All right, so we just used the second formula here, right? Now we're going to do our chi-squared table, okay? So in this case...
Can I ask a quick question?
Yes, quick question.
R1C1, what is that formula called? R1C1.
This is the expected count formula, I guess you could call it that. Yeah. So these are the expected counts under the null hypothesis. I don't know it has an official name, but that's what it is.
And then what is this other formula called?
The other one's called my chi-squared formula. Okay? All right, so we're going to use the chi-squared formula now. Okay? The chi-squared formula says the observed. So I observed, and here's where you want to use parentheses. If you don't use parentheses, you will use all the right numbers and you will get the wrong answer. Okay? So the parentheses are the observed 35 males minus the expected 31.5. I'm going to square that, raised to the second power, and I'm going to divide by the expected. Okay? Equals the parenthesis observed minus the expected squared divided by the expected. Okay? Equals the observed 20 minus the expected 23 divided by the expected equals the observed 40 minus the expected squared divided by the expected. Okay? All right, so I've just done this formula. What have I neglected to do so far? What does this mean?
So,
That means find the sum, okay? So I need the sum, and what am I finding the sum of? That entire table, okay? So if I click on my sum here, I'm going to add up this entire table. Okay? So I got a sum of 1.55. Okay? All right, so now the next step is what? So step number 5 is find the p-value. Okay, now, I really wish I had a camera that would focus. Let me try something here. I'm going to see if I can focus this a little bit better. Okay? There are some buttons here. Oh, it focused. How about that? Who knew? Okay, so it does focus. Okay, let me turn this up.
Yay.
Okay, sorry for those not knowing how to use the camera. All right, so let's talk a little bit about the chi-square test. Okay, the chi-square distribution. Okay, the chi-square distribution, number one, it is not symmetric. Okay, unlike the normal distribution, this one is not symmetric. Okay, number two, the shape changes based on degrees of freedom. Okay? And I'm going to erase this. Number three, the degrees of freedom has a different formula. It does. Okay? Degrees of freedom equals the number of rows minus 1 times the number of columns minus 1. It's not too bad. Okay? Number of rows minus 1 times the number of columns minus 1. Okay? I'm sorry, but here we go. Okay? Now, let me show you. When I say that it changes shape, I mean it changes shape. Okay? Let me open up this chi-square distribution. Okay? Now look at this. For some reason, and I don't know why they do this, okay? They use the letter K instead of DF for degrees of freedom. Okay? So, if your degrees of freedom equals 1, it's the yellow line. Does that look like a bell curve to you? Not even close.
Each degree of formula has a different what?
Different shape. Okay? If your degrees of freedom are 2, it's the green line. Okay? Also starts high, then it goes low again. If your degrees of freedom is 3, it no longer starts high, it's this light blue line. It starts at 0, goes up, and it's that blue line. If it's 4, it's the dark blue line. 6, it's the purple line. 9, it's the red line. Okay? So this really changes, okay? Now, so typically, let me stop sharing for a second. Typically, if it's greater than 2, you're going to see a chi-square distribution. It's going to look something like that, okay? This value here is 0, okay?
You said if it's blank, you'll see a degree of freedom that looks like that. What was blank?
If it's greater than 2.
Greater than 2.
Yeah, now let's back up again, okay? We've got a 2 by 2 table, right? How many rows do I have? 2 minus 1 is 1. 2 minus 1 is, how many columns? 2 minus 1 is 1 times 1 is 1, okay? So if it has degrees of freedom equal to 1, it looks like this, okay? Oh, it's on there, okay? So this is actually what ours looks like, okay? Now, let me ask you something. Let's go back for a second, okay? When we're looking at our table, what we're trying to do is we're taking our observed minus our expected. If I get a value, if my chi-squared value, if these two numbers are close, and I subtract them, what would they be? If there was no difference between your observed and your expected, what would they be? It would be 0, okay? So 0 indicates no difference, okay? If these are far apart, what's going to happen to your sum? It's going to be large, okay? So large indicates difference, okay? So if I get a large value out here, this is the case where we're going to always, so the chi-squared is always a one-tail test, okay? Typically, most of the other tests are two-tailed, but the chi-square is 1. Okay, so if I get a 0, that means they're not different. If I get a large sum, that means they're different. Okay, so 0 would indicate independent. Large difference would indicate dependent. Or not. Shit, I did it again. Not independent.
Wait.
0, a sum close to 0 would indicate it's independent. A large sum would indicate it's not independent. And the question is, what is large? Is 1.55 large, right? Probably don't know, and I don't know either. Actually, I do know, but I'm
So
pretending I don't know.
you would just say not independent. You do not say dependent.
You do not say dependent, okay? We don't say it's dependent because there could be some working variables, which is sexism or racism or something like that, okay? All right. So, so does this make sense conceptually? Kind of. Okay. All right. So the idea here is we're going to reject if the sum is large, which also means your p-value will be low. Okay? Those basically say the same thing. If your p-value is large, if your sum is large, your p-value will be small. Okay? So that's what's going on. Now, gosh, maybe I should, they have a chi-square, I don't know. You know, I should just pass out my formula sheet because you're going to use this on the test anyway, right?
No, we gotta have the whole thing memorized.
Yeah, you're going to memorize the whole chi-square table.
It's the same one that you.
No.
This one.
Yeah, you got
I
it
think I
already.
have one.
Yeah, you got it already. It's the same as yesterday, nothing changed. Okay, so let's go ahead and we're going to look at our chi-square table. Oh, actually, maybe.
Good.
Well, here, I'm going to do it this way. It'll be easier. Okay, so you should have a chi-square table, all except for, it's not gonna remember.
Wait, so there's only one tail, but why they're showing two tails on the like,
Oh my gosh, this is gonna drive me crazy. Okay, while this is doing, we're going to show you the table here on the. Okay, so turn to the chi-square table. It's the last table. Okay, now, just a moment. It's taking too long. All right. Okay, so hopefully you can see this here. Go down. There you go. Okay, so the idea here is we're going to be doing a right-tailed test. Okay, this will always be a right-tailed test. Now, it does tell you how to do a two-tailed test. It's a little bit complicated, and I don't think we're going to do a left-tailed test ever in this class because a left tail means means it is independent, right? So the right tail is what we're going to be concerned about. Okay, so we have 1 degree of freedom, right? Okay. Now the idea here is I got a value of 1.55, right? So just like with the T table, we're going to be on the top line here. Where does 1.55 fit on this table? It's right in between these two numbers here, right? Okay. So your p-value, this is funny, is between what and what? 0.10 and 0.90, right?
Yeah.
Now we forgot to mention what our alpha was in the last one here.
I think the degrees of freedom is what?
Degrees of freedom is 1. So we're on the top line, 1 degree of freedom. We're finding 1.55. It's in between 0.10 and 0.90. Okay? So if I'm using the table, I can't get an exact value on my p-value.
That's a pretty big range.
It's a really big range. Okay? So with the chart, all we can say is 0.10 less than p-value less than 0.90. Okay, now what are we assuming our alpha is? We forgot to mention that. Alpha is 0.05. Okay, so based on the chart, question number 6 is reject or not, right? So do I reject or do I not reject? Would you say, Sandra?
You say reject, you say some.
Well, I'm not talking about the sum at the moment. So is the p-value low?
No.
So therefore I do not reject. Okay? Now with the computer, I can get a better value. If you were Bill Gates and you wanted to come up with a command to find out the p-value for a chi-square distribution, what would you call it?
X.
Equals x, that would be close because it looks like an x. Chi, right? Equals chi-square distribution. Do you want to do a left-tailed test or a right-tailed test?
Right.
We are always going to do a right-tailed test on this test, okay? So it's asking for x. What do you think x is? The sum. Sum in this case is 1.559, right? And how many degrees of freedom do I have?
1.
1 degree of freedom. Okay. So my p-value hopefully is in between 10% and 90%, and it is 21%. Okay. So in either case, whether you do it with the chart or whether you do it with the computer, you do not reject. Okay? Does that make sense? What'd you say? Okay? Now, the conclusion is what? What's the conclusion? Chandler?
I'm just confused. You said reject if the sum is large, and if the sum is large, the p-value is low.
So is my sum large? No, it's close to 0, right?
So that's why we're not.
So we're not rejecting. Okay? Now, we can also talk about what our sum would have to be on this problem. But anyway, let's go with the conclusion first. What's the conclusion? Say it louder, Sandra. So answer this question. Is it fair to conclude discrimination? There is not enough evidence of discrimination.
That's it?
Yes.
There's not enough evidence.
Okay. Now, I knew this was going to take a long time. We've got 3 minutes left. Normally, I try to cover chapter 6. Chapter 6 is related to chapter 25. And so save this spreadsheet because we are going to use it, this exact same spreadsheet that you have. So save it, email it to yourself or something. We're going to start tomorrow's lecture at step 7, which covers chapter 6, which is on Simpson's paradox. Okay? I can send this to you. Hopefully I will remember today. I will try to walk back to the other one and I'll try to post that one as well. But tell you what, I will save it right now. Before I do that, now, let me just say, so maybe I shouldn't have told you reject if the sum is large. Just think of the p-value the same way as you always have. Okay? Now, how do you know the sum is large? If your sum was large, what value is considered large on 1 degree of freedom? Now you're going to get that on your chart. Okay? What's my alpha in this case? 0.05. So with 1 degree of freedom, if my alpha is 0.05, your sum would have to be larger than 3.841. If you got a sum that was more than 3.841, then your sum would be too big. Your p-value would therefore be less than 0.05. Does that make sense? Okay. So if I were to draw this on the picture, if it was greater than 3.841, that would mean I would reject. Okay. Yeah, so let me draw a picture. So, and I'm going to try to draw this accurately this time, okay? Because we've only got 1 degree of freedom, correct? Okay? So, with 1 degree of freedom, my chi-square distribution looks like this, right? Okay? So the idea here is, you can still see that, this is a bad marker though. If I get a value greater than 3.841, this is my alpha equals 0.05. Okay? So if I got a value in here, let's say I got a value of 4.5, let's say, that's my reject. The white area is do not reject. Okay? I got a value of 1.55, I do not reject. Okay? So this is how you find the value. This is what we would call the critical value. Okay? Now be glad that I'm not teaching you how to do a left tail test because that's really confusing. So you guys are lucky. You can do a left tail test. It doesn't apply for our independent test. If it did, I'd have to show you that. Okay? So this is the thing that you can use. I will take my formula sheets back, and you've got them already from yesterday, right? The only thing different is
Put it in all the forms.
yeah. It's got this one though. Okay. All right. So the quiz tomorrow I haven't decided. I might let you use the computer for the quiz tomorrow. I might not.
I say no computer.
Computer?
I can't figure it out still. I'm still back on the first part of the chi-square test, entering that, so.
All right, so, and then can I get your shadow? All right, so anyways, quiz tomorrow is on chapter 25. We will cover chapter 6 tomorrow in class. I don't know why
So
they
homework's
put,
still only
6 and 25 should go together because they're related to each other.
We're only doing homework for 25, right?
The homework is on chapter 25, that's
Thank
correct.
you.
Okay? Thanks.